Hello everyone, welcome back to another MCR3U1 video, and we are continuing on chapter 5 today with trigonometric identities. Identities can get quite complex and lengthy to solve, so I really suggest you practice even after the example videos, because the best way to understand and get better at solving identities is by rinse and repeat and keep solving more and more of them. This practice can be found on pages 310 to 311 for today's topic on section 5.5. So let's get started. In this lesson, we want to, of course, prove trigonometric identities by using these methods. The first one being rewriting the expression using well-known identities, which we'll cover in the next few slides. Second is rewriting the identity in terms of x, y, and z, and we will see how we get this x, y, and z variables in the next slide, or in the next few slides, not exactly in the next slide. And lastly is by factoring and manipulating each side of the expression to show that left side equals right side. That is probably the most important thing about this about solving identities. We need to make sure that the left side equals the right side. That's the whole point. We also want to note any restrictions we find on our angle throughout the question to avoid denominators equaling to 0 when working with rationals. Here are some well-known identities we want to memorize to help us solve more complex identities. Well, before we go on to exactly what these identities are, let's go over the definition of what an identity actually is. So, an identity is a mathematical statement that is true for all values of the given variable. So, what does this mean? This means that no matter what numbers you decide to substitute into our variables, the left side of the expression will evaluate to the same number as the right side. And again, we want to state the restrictions at the end. So no matter what expression we have on the left equaling what expression we have on the right, here could be a bunch of variables, here could be a bunch of variables. We plug in any number for these variables, the left side is going to equal the right side once we simplify or once we evaluate. So here's the table of identities we need to know. We've looked at reciprocal ratios already, so I won't go over them too much, but just take note of the restrictions, which I'll go over right now. So we have, again, cosecant theta equals 1 over sine theta, but remember that we don't want any denominators equaling 0, so we don't want sine of theta to equal 0, and therefore theta cannot be 0 or 180, because if we do sine of 0 or sine of 180, it will give us 0, and we'll get 1 over 0, which will give us an undefined expression. Secant theta equals 1 over cos theta, so cos theta cannot be 0, so theta has these restrictions of 90 and 270. And for cotangent of theta, we equals 1 over tan of theta, so again, tan of theta cannot be equal to 0, which means that theta cannot be equal to 0 or 180, because tan of 0 or tan of 180 will give us 0. Next, we have the quotient identities, where we have a rational expression with a trig ratio on the denominator and numerator. So let's go through these. First one, we have tan of theta gives us tan of theta equals tan of theta equals sine of theta over cos of theta. That's an identity we want to remember, and we'll actually prove this identity in the next couple slides. And here we have cosine of theta in the denominator, so again, we can't have cosine of theta equaling 0, so the restrictions on theta will be 90 and 270. And for cotangent of theta, this will equal cos of theta over sine of theta, and you can see it's kind of just the reciprocal of tan of theta, right? Because remember, as we have here, cotangent of theta equals 1 over tangent of theta, and if tangent of theta equals sine of theta over cos of theta, this will give us 1 all over sine of theta over cos of theta, which is the same thing as saying 1 times the reciprocal of the divisor, which is cos of theta over sine of theta, which will give us cos of theta over sine of theta, which will be equal to cotangent of theta, right? So that's cotangent. And again, since we have the reciprocal now, we have sine of theta on the denominator. Sine of theta cannot be 0, so our restrictions on theta will be 0 and 180. Okay. Lastly, we want to remember the Pythagorean identities. The first Pythagorean identity we have is sine of squared theta equals cosine of squared theta equals 1. Okay, so this is an identity we'll be using a lot to solve our identity problems because we'll have a lot of sine squared or cos squared in our questions, and even a lot of our common identities have sine and cosine, so we'll use this equation a lot. The other two we want to remember are 1 plus tan squared of theta equals secant squared of theta, and 1 plus cotangent squared theta equals cosecant squared theta. And remember, we can rearrange these to look differently, and it might help us in a particular question. So for example, this 1 plus tan squared theta equals secant squared theta will be the same as saying if we subtract 1 from each side, so minus 1 and minus 1, so it'll be plus here, these will cancel out, and we'll be left with tan squared theta equals secant squared theta minus 1. Same thing here on the bottom. If we subtract the 1 from each side, we'll be left with cotangent squared theta equals cosecant squared theta minus 1. Right? And this might help us because, for example, in a question, if we, somewhere in the question, right, we have our left side and our right side, but on our left side we have tan squared theta times something something, and we want to switch this to in terms of secant, we have this identity, but the top identity we have 1 plus tan squared theta equals secant squared theta, so we want to isolate for tan squared theta, and so we can turn it into this and substitute secant squared theta minus 1 into our expression. Okay, so we kind of switch them around. Now let's move on to proving identities using x, y, and z. This will give us an understanding about how identities work and how the left side of an identity will equal the right side. So, as we know, if we plot a point P with an x and y coordinate on the Cartesian plane, we can create our right angle triangle using the terminal arm, the x-axis, which in this case is also the initial arm, but it also depends on what quadrant we're in, so it might not be the initial arm, and a third side connecting the terminal arm to our x-axis side of the triangle. And the side lengths of the triangle will be the absolute values of the coordinates making up point P, and the hypotenuse will be the root of x squared plus y squared, because remember, r is going to be equal to square root of x squared plus y squared, and the side length of this side of the triangle is x, right, the absolute value of the x coordinate of P, and this side length is the y value of P, the absolute value. And our angle theta will go from our initial arm, which is at the positive x coordinate, to our terminal arm, which is the hypotenuse of our triangle. So we're going again, starting at our initial arm, going to our terminal arm, and that's our angle theta. And using this right triangle, we can substitute the ratios of theta for its equivalent expressions in terms of x, y, and r, and we can solve the identities that way. So let's cover these 4 examples that I have here on the right, and you'll see this happening. Okay. So the first one, we have tan theta equals sine theta over cos theta, which is one of the identities we just learned in the last slide. And so let's see what we can substitute into this. Using theta, this angle, from our right angle triangle we drew on the right, and I actually forgot to put the right angle sign here. What is tan theta? Well, if we remember, tan theta is going to equal side opposite to theta over side adjacent to theta. What's our side opposite to theta? It's going to be y. And what's our side adjacent to theta? It's going to be x. Right? So we can substitute y over x for tan theta. And we can do the same for sine theta and cos theta. So sine theta, we know it's going to be opposite over hypotenuse. And in this case, opposite is y, and hypotenuse r, all over cos theta, which, remember, again, is adjacent over hypotenuse. Adjacent to theta, we have x, and the hypotenuse, of course, is r. Now, if we keep simplifying this, on the right side, remember, let's keep going. On the right side, we have y over r over divided by x over r. But remember, if we have a rational, right, divided by another rational, it'll be the same as the first rational, which is y over r, multiplied by the reciprocal of the second rational, which is x over r. So the reciprocal of that will be r over x. And if we multiply these together, we'll have yr on the top and rx on the bottom, and we can actually cancel out this r, and it will just give us y over x, which is equal to the left side. So this identity is proven. Tan of theta does equal sine theta over cos theta. Our left side equals our right side. And that's it. Okay, so let's prove the rest of these by just, again, substituting x, y, and r. So cosecant of theta, again, is the reciprocal of sine of theta. So if sine of theta is y over r, this is r over y. And sine of theta, again, is y over r. And remember, 1 divided by y plus r is the same as 1 times r over y. And so r over y will equal r over y. So our left side equals the right side. Next, we have 1 plus tan squared theta plus secant squared theta. So this is the same thing as saying tan of theta all squared, right? So we can rewrite this as 1 plus tan of theta all squared, just to visualize what's going on better. And we can sub in our x and y and r values to tan and secant of theta. So tan of theta will be y over x, as we saw before, all squared, which equals secant of theta, which is the reciprocal of cosine. It's going to be r over x all squared. Right? Let me just separate this. Let's continue. Now we will use the exponent to square the top and the bottom. So r squared over x squared equals y squared over x squared. And this 1, we can actually turn it into an x squared over x squared, right? Because remember, a number on the top divided by the same number at the bottom will always give us 1. And we do this so we can have a common denominator of x squared, and we can actually add the numerators, which will give us x squared plus y squared plus x squared equals r squared over x squared, right? And we'll go up here. And now from here, if you remember, r squared, right, in our triangle is going to equal x squared plus y squared because of Pythagorean theorem. If you have a right angle triangle, x squared plus y squared is going to give us the hypotenuse squared. So we can actually change this x squared plus y squared into an r squared. And we'll have r squared over x squared equals r squared over x squared. And that will be our answer. Lastly, we have, it looks like I repeated that question, so I guess we'll skip this one and we'll just carry on. Here are a couple more common identities that are useful to know, but might not be used so much in this course, but maybe in future math courses. And we have the double angle and the addition and subtraction identities, which are a little more complicated and harder to remember, but yet come in very handy. Our first 3 identities are the double angle, and we call them this because we can see that on the left side of each identity, we have a primary ratio, a primary ratio of angle 2 times theta. So multiplying our angle theta by 2. That's why we call it double angle. And the three we want to remember are sine, cosine, and tangent double angle identities. So let's just go through them real quick. So we have sine of 2 theta. It's going to equal 2 sine theta cos theta. So that might be a little complicated to kind of remember at first, but the more you do questions, the more you use this identity, you will remember it easier and easier. Then we have cos 2 theta will give us cos squared theta minus sine squared theta, which also equals 2 times cos squared theta minus 1, which also equals 1 minus 2 sine squared theta. So this is because if we're here at cos squared theta minus sine squared theta, if we remember our Pythagorean identity, which I said we're going to use a lot, so here we go, we're using it here. 1 equals sine squared theta plus cos squared theta. If we can remember this from previous slides, we can actually rearrange this, right? We can subtract sine squared theta from each side, right? Or theta, and we will actually get cos 1 minus sine squared theta equals cos squared theta, right? And this is our identity just rearranged. And if we actually substitute this into cos squared theta minus sine squared theta, we will get 1 minus sine squared theta minus sine squared theta, right? We just substituted it for this cos squared theta. And now we have 1 minus sine squared theta minus sine squared theta, which is 1 minus 2 sine squared theta, which is this right here. That's why it also equals 1 minus sine squared theta. And if we do the opposite, if up here we actually rearrange for sine squared theta, right? So we subtract cos squared theta from each side, minus cos squared theta. The cos squared theta will cancel out and it'll give us 1 minus cos squared theta equals sine squared theta. And if we substitute it into this expression right here, we will get cos squared theta minus 1 minus cos squared theta. And if we use the distributive property, we can get cos squared theta minus 1 plus cos squared theta, which will give us 2 cos squared theta minus 1, which is this expression right here, right? So they're all equivalent. They all equal cos of 2 theta, okay? And we can go through the last one, which is tangent. And this is probably the most complicated one to remember, because this one you can actually just remember the first expression, and you can use the Pythagorean theorem or the Pythagorean identity to get the rest, right? And the sign you also have to memorize, but it's kind of easier. But tan of 2 theta is going to give us 2 tan theta all over 1 minus tan squared theta, right? So it's a little more complicated, but we can still remember it and it'll be all right, okay? Now, our addition and subtraction identities get their name from the fact that we're adding and subtracting two angles, A and B in this case, and we are taking the primary ratio of the result, right? So from this lesson, we want to learn the sine and cosine addition and subtraction identities. So let's just go through them. Here are the sine, here are the cosine. And again, we're adding the angles and we're taking the sine of the result, right? But if we just had them in this format of sine of A, angle A plus angle B, this is actually going to equal sine of A times cosine of B plus cosine of A times sine of B. Now, our subtraction, sine of angle A minus angle B, is going to equal sine of A, the first angle, times cosine of B, the second angle, minus cosine of A, the first angle, right, times sine of B, the second angle. And if we move on to the cosine, we have cosine of A plus B. It's going to give us cosine of A times cosine of B minus sine of A times sine of B, and cosine of A minus B will equals cosine of A times cosine of B plus sine of A times sine of B. And that's pretty much it. These are a little more complicated to remember because there's just so many terms, or not so many terms, just like it's hard to remember what angle goes where and where the sine and cosine go. But the way I like to remember it is in the sine addition and subtraction identities, the sine of the angle, the sign between the angles, so if it's addition or subtraction, will be the same sign, right, in the right side of the identity, right? So in the addition identity of sine, we're adding these two terms, and in the subtraction identity, we're subtracting the two terms. And in cosine, it's the opposite sign. So if we have addition, right, the addition identity of cosine, we're going to subtract the two terms on the right side. And if we have a subtraction, we're going to add the two terms on the right side. So that's the way I like to remember it. Sine stays the same, and cosine sine changes, right? It's the opposite. And the way I like to remember sine for the angles and the sine and cosine, it's sine and cos plus cos and sine, right? And sine and cos minus cos and sine. So we have alternating ratios, right? So we have sine and cos, whereas for cosine, we're always having cosine first, if that makes sense. So for sine, we have sine and cos, and for cosine, we always have cos and cos, and then sine and sine, and sine and sine. And the angles are always they're never the same on each term. So the first term here is sine of A times cos of B, right? If it was the same, it would be sine of A times cos of A. But it's always A, then B, A, then B, A, then B, A, then B, A, B, A, B, A, B, A, B, right? So that's also a little trick to help you remember. You always alternate the angle. Sine, you keep the same sign. Cosine, you change the sign to the opposite sign. And for cosine, it's cos first, then sine. And for sine, it's alternating, so sine and cos, and then cos and sine, and then sine and cos, cos and sine, right? So those are a few little tricks to help you remember those. This is a quick summary of the different approaches and methods we want to use to prove identities. These are not in any particular order, as we can use these in different orders for different types of questions, and we might even use a few of these methods in a we might not even use a few of these methods in a particular questions. It truly just depends on the identity. So to prove an identity to be true, we must show that the left side equals the right side, as we said before, by manipulating one or both of the sides of the equations. But remember, we don't want to switch terms from one side to another. We want to keep everything on its own side because we want to prove that the current left side equals the current right side, right? So if we have something like sine theta plus cos theta equals tan theta, let's say times cos theta plus cos theta, right? We don't want to, for example, subtract sine from each side, right? So we can cancel this one out and we kind of switch it to the other side. We don't want to do that. We want to keep everything on the same side and kind of substitute our well-known identities in. So what do we want to do in this case, for example, is switch tan of theta, right, by its identity, which is sine of theta over cosine of theta. And then we can see that these cosines cancel out, and we'll have sine of theta plus cos of theta equals sine of theta plus cos of theta, right? So we want to keep everything on the same side. We just want to use the common identities to solve the questions and these methods that I'll continue to go over. So next method, we want to rewrite the trig ratios into terms of x, y, and z, and then simplify it just like we did a couple slides back. And sometimes if so we want to do this sometimes if the question is not too complicated, because we can just sub in the variable and see if each side matches, and we don't really have to deal with remembering all the common identities and kind of substituting them in like I just did up here. Next approach, we want to rewrite the expression in terms of sine and cosine and then simplify. And this is sometimes preferred because there's a lot of common identities that involve sine and cosine, and we can substitute these in and hopefully cancel out terms until our left side equals our right side. Next, we can apply the Pythagorean identity where appropriate, and this identity is used, again, like I said, often because if there's ever a sine squared theta or a cos squared theta in the question, we can use this identity to change that term, like I did in a couple slides back. Remember, it's 1 equals sine squared theta plus cos squared theta, right? And we can kind of rearrange this identity and use this to substitute it into our current question to solve for left side and equals right side, you know? And lastly, we can use or we can find a common denominator or factor when appropriate. And of course, as it says in the bottom, we want to use all of these methods, again, in no particular order, and put them all together to prove our identities. And that is it for the video, guys. I hope it was useful and you were able to learn everything well, and I'll see you in the example video.